There are two parts to dynamics. Just like when we do ordinary, say, quantum field theory perturbatively, we pick a sum over Feynman diagrams organized by some power series approximation. And then in each diagram, we sum over the unconstrained energy and momentum. And basically, we do the same here, only the first part, which is analogous to a Feynman diagram, is picking a process which develops into a causal set with energy and momentum. So here is, given that we do the first, here is the analog of the Feynman amplitude. The amplitude for some total process P is the product over all the unconstrained momenta, a delta function at each event, which tells us that energy and momentum are conserved there, and an amplitude Q, which has what I was speaking about the potential energy related to variety, which will be related to Bohm's potential and the kinetic energy. So this is the complete definition of the theory. And notice there's no H bar anywhere because there's no canonically conjugate position relative to the momentum. There's no commutation relations, there's no uncertainty principle. And for people who like to worry about non-locality, there is simply non-locality and no locality either. There's no mention of embedding of these causal processes in space. So there's no locality, there's no non-locality. These distinctions are going to emerge when space emerges, which will be something that happens dynamically in a certain limit, which we'll be discussing. Basically a stationary phase approximation. Okay, now to tell you a little bit more about how the potential energy is constructed, here's a little bit about variety. So variety is a measure of complexity, but it's complexity in the mind of how distinct are the subsystems and how distinct are the different views. So imagine that you're in a city, an old, great city like Lisbon, and you know it well. Somebody could put you down anywhere on any corner, take off a blindfold, and you know instantly where you are, because every corner is distinct. The view from every corner from down any street is distinct of any other nearly, because it's an old, great city built up chaotically. Whereas if we put you down in a suburb of Toronto, every corner looks like every other corner, and you wouldn't know where you are. So the first kind of situation is what we call a high variety situation. And the second kind of situation is a low variety situation. And we have a measure of variety. One way, if the situation or if the system that we're talking about is causal graphs, we sum over all the pairs of events. And for every event, we count outward 1 step, 2 steps, 3 steps, 4 steps at each of the 2 events. And the lowest number that we count to, such that that subset around the first event is not the same, is not isomorphic to the subset around the second event. We call them distinctive at level K, if K is a number of steps. And then we just sum over 1 over K. And that gives us the notion of the variety of the set. Okay. And by the way, I'm happy to take questions anytime. So these are, biology produces lots and lots of examples of causal networks. These happen to be pictures of genetic regulatory networks developed by some of the people at Santa Fe. And if you measure their variety, they're often high variety sets. The kind of lattices that we physicists, condensed matter physicists, or particle physicists like to work with are very low variety sets. It's interesting to try to generate numerically high variety sets. And there's a collaboration at Microsoft Research led by Jaron Lanier that I've been very honored to be part of. And part of what we've done, and this is, you can ask him the questions why hidden variable theory. Well, it should be clear from this talk. We have to generate very high variety graphs and study them. So that's 1,000 node high variety graph, which is the biggest one we've been able to construct. It has an unusual degree distribution. And this is just to restate the basic construction. The basic construction is we have given two views of the past of some event. We have a metric Hij, which is the distinction between them. From that, we construct the variety, and the variety is part of the action principle. It's basically analogous to the potential energy. So in words and in concepts, it's very easy. We're very Leibnizian, and we're asking the universe to develop and increase by increasing its variety. Okay, so here we're going to talk more about the action. Here's the half integral, as I defined before. And let me note that the Hamiltonian has its kinetic energy and potential energy. And there are free parameters, G and G prime. And it's going to turn out, not surprisingly, that G prime over G squared is related to H bar squared over M. That will not surprise people who work with hidden variable theories. Oh, wow, it's working. And here's, maybe I won't dwell on this given the time, but here is the sum of how the details look in the non-relativistic version of the theory, which is the one I'm mostly talking about here. P lower k upper I is the energy momentum transferred from event K to event I, and that's what the causal network is constructed from, is first constructing the network and then dividing up pieces of energy and momentum and distributing them across the network as dictated by the equations of motion that come from that action principle. Okay. So here's the cheap trick, because everybody, when they're trying to do something new, finds a cheap trick. The cheap trick is, I've been saying there's no space-time. But for each event, there's a constraint, which is the conservation of energy and momentum at that event. And I can exponentiate that constraint by introducing Lagrange multiplier, Z, or Z, let's call it Z, and writing delta of the constraint as integral over dz of e to the I z times the constraint. And Z is in the dual space to momentum space, in other words, configuration space. So the Z's are a way to get an emergent notion of an embedding in space-time dual to momentum space into the theory. So that's kind of the cheap trick. And then we go to the stationary phase approximation. There's here a number of details I'm skipping. We split the fluctuations into transverse and longitudinal. The longitudinal, of course, are the gradient of a phase. So that's how we address the issue of how to get some of the momentum coded as the gradient of a phase. The other transverse degrees of freedom of the momentum we integrate over and end up with expressions just related to the gradient of the phase. And I'm happy to come back to details. It's a few stages of calculation. But here's the key point. The action principle had three parts. The Lagrange multiplier Z times the constraint, which is sum over momentum. What I'm calling the causal part of the variety, which is the kinetic energy, and that involves the differences between the views of causally related events, and the acausal part, which sums over the differences of views of not causally related events. And they go down to, after you do all the integrating out you can do, and you introduce a probability distribution, rho, to represent an ensemble of such systems. And then the action principle becomes rho, the integral of rho times what looks like the Hamilton-Jacobi equation with the additional potential, which, not surprisingly turns out to be the Bohmian potential. The kinetic energy goes into the p squared, which is the gradient of a phase squared. The potential energy goes into the Bohmian potential. And the role of the Lagrange multiplier creates the symplectic structure In other words, the structure of rho S star. And that, as I'm sure many of you know better than me, generates when you vary at the real and imaginary parts of the Schrodinger equation. So I think that's a step that will be very familiar to people. But let me emphasize something important, which is that there are corrections. So there is a delta U Q, which emerges, and these are maybe it's best if I come back and say what the expansion turns out to be in, but there's a natural expansion. Well, I'll say it in terms of basically the number. When I introduced the probability distribution, I posited a kind of collection of similar systems, and I average over them, they become an ensemble. And N is the size of the ensemble that I use to generate probability distribution. So we see that basically 1 over N to the 2 over the dimension is fixing the size of these corrections. And those are types of corrections that violate unitarity, but they're consistent with probability conservation. And they've been studied by different people, so that's not new, but it's important to emphasize they emerge from here. Okay, you are much more expert about this than I am, but what I imagine is that in the quantum laboratories that people are developing, there are some systems which entangle states of some combinatorial complexity, which the question is how many natural such states, copies of the states, will exist. If you're talking about something like a hydrogen atom, there's a large ensemble of natural or pre-existing ensembles that anything we work with in the laboratory will be a copy of and will be part of an ensemble. But it's pretty clear that with the technologies that we have, like quantum dots and many other things you know about better than me, we can construct states which, if we ask, is there any isomorphic entangled state anywhere created naturally, the answer would be unlikely. So that's the kind of thing that I'm thinking of. And then there's a science fiction joke that comes at the end of that that lets you work out for yourself.